Last time we were talking about interactions between systems, thermal interactions, mechanical interactions. Today I want to continue along that vein. I want to just review a little bit about what we said last time. So we have two systems interacting, system A and system A prime. We found that the condition for equilibrium was that the derivative of the log of omega with respect to E would be equal to the derivative of the log of omega prime with respect to E prime. So this is the condition for equilibrium. What we did at that point is to define the term beta of E, and we're going to use a squiggle for E is equal to beta prime of E prime, where we define beta of E as d log omega dE. This is the condition that is going to maximize the probability. At the same time, we can introduce a dimensionless parameter related to beta. We'll call it T. That should be fairly suggestive in a thermal course, such that KT is defined as 1 over beta. Now we'll elaborate on this as we go deeper into it. From before, you might remember that we also defined 1 over T as the derivative, the partial derivative of entropy with respect to energy. And we're going to take advantage of that relationship as well. You might remember we've defined entropy as K log omega, K times the log of the number of accessible states. And so another way we can describe the maximum probability is to say that at equilibrium, S plus S prime, the entropy of system A prime, is going to be a maximum. For those who are ahead in terms of learning about thermodynamics, you might recognize that that has something to do with the second law, and we'll get into that more deeply as well. What we also mean by this, if beta equals beta prime, that also means T is equal to T prime. So if we wanted to call T an absolute temperature, which we will later on, the condition for thermal equilibrium is that two systems are at the same temperature. We're kind of stepping ahead of the game, but that's okay. We'll get there anyway. What we want to do now is we're going to get in the weeds a little bit and talk about the approach to thermal equilibrium. Now, first of all, we know that in situations where you have large numbers of accessible states, the probability distribution is going to be extremely sharp. And by that we can say that when E has some value, E tilde, that's going to be the situation that makes the probability a maximum. In other words, it's a very highly probable situation, and E prime then would just be E naught, the total energy of the combined system, minus E tilde. And we'll use tilde here as well. Now, because before thermal contact, the two systems may have completely different energies, but once they become in contact, they're going to exchange energy until we have a completely equilibrium situation such that we can say that maybe my final energy is going to be equal to my most probable situation, and therefore the final energy for system A is going to be equal to just E naught minus E final tilde. So this sort of all fits together. Or if we like to say this, we're going to say that beta as a function of the final energy for system A is going to be equal to beta prime, the final energy for system A prime. Moreover, I can say that the entropy as a function of E, when I combine the two entropies, I should be getting a maximum such that the final entropies are going to be greater than the initial entropies of the system. Again, sort of reflexive of the second law. In fact, we can say delta S plus delta S prime the differences in entropy from the beginning or initial to the final is always going to be greater than or equal to 0. Let's take this a little bit further. By conservation of energy, we know that if I were to add the initial energies and it would have to be that the sum of the two energies initially has to be equal to the sum of the two energies at the end of the experiment. That being the case, since all the external parameters are remaining constant, in other words, there is no mechanical interaction in this case, only a thermal interaction, we can very easily see that the heat exchanged between the two systems, EF minus EI, or I should say the heat, the change in heat from the system A, and I can write the change in heat or thermal energy from system A prime in this way, says that it has to be, by conservation of energy, that the heat that is gained by system A is going to be the heat that's lost by system A prime, or vice versa. Again, this all relates to the first law, the conservation of energy. No big surprise here. Physically, what this is saying is that hotter systems are going to give off thermal energy or heat to cooler systems. We don't know of an exception to that in the universe. So, in equilibrium, we basically, or when we talk about equilibrium situations, there are two situations that can arise. One, initially, the energies of both systems are exactly the same, which says if that's the case, if E initial is equal to E initial prime, that also says that beta initial is equal to beta initial prime. That means that T initial is equal to T initial. In other words, the systems are at equilibrium to begin with, and they're going to stay in equilibrium for all eternity. That's just the way it's going to be. More generally, it will be the case that the two temperatures, or the two betas, are not equal to begin with. And what's going to happen is we're going to have a transfer of energy, thermal energy, from the hotter, or the one that at the higher temperature, to the one at lower temperature, until both temperatures are equalized, and we say that thermal equilibrium is attained. So we've come this far without really discussing temperature. But as you see, it's implied in all of our statistical analysis until we finally admit that, well, we have a quantity called beta that is, that in a situation where two systems are in equilibrium, the betas are the same, and we define beta as 1 over kT, where T will turn out to be the absolute temperature. So now that we want to bring temperature into the mix, into our study of statistical mechanics, let's do a little bit of a detour into temperature, and we're going to discuss actually yet another law of thermodynamics. So there are a number of ways that we can discuss temperature. We're going to start with the more statistical way, and then we'll get to something a little bit more hot and cold as time goes on. So suppose we have, in this case, suppose we have three systems. System A, System B, and System C. So I have three systems. I'm putting them into thermal contact so that they reach equilibrium. In fact, I'm going to put A and C in thermal contact until they reach equilibrium. That means that beta A will be equal to beta C. And then I'm going to have System B and C in thermal contact until they reach equilibrium as well, so that beta B is equal to beta C. And of course, by transitivity, we conclude that, of course, beta A must be equal to beta leads us to something that we call the Zeroth law of thermodynamics, which says that if I have two systems in thermal equilibrium with a third, they must be in thermal equilibrium with each other. Sounds kind of like the old transitivity postulate from geometry. But it works in exactly the same way. The reason this is important, it sounds like an obvious kind of law of physics. But the reason this is important is we can look at this third entity, this third system, as long as it has many fewer degrees of freedom, less than the other two systems, we can call that third system a thermometer. That's what enables us to measure an absolute temperature. So this test system, maybe we'll call it, let's call this system M. This is a test system that more commonly is called a thermometer. Without the Zeroth law, you could not have a thermometer, would make no sense whatsoever. So here we have some macroscopic parameter theta, which varies in appreciable amounts when M is brought into thermal contact with some other system, like maybe A or B. And as I said before, M has many fewer degrees of freedom less than systems A or systems B. That's crucial in order to use M as a thermometer device. So we have some examples of this. Take mercury in a glass tube. That's your common mercury thermometer. What happens is, as the temperature goes up, the height of mercury in the tube also goes up. So the temperature is proportional to the height of mercury liquid in a tube. So we call this a mercury in a glass thermometer. Another example, suppose we have a gas in a bulb that we keep at constant volume. Theta then says that the temperature is proportional to the pressure in that bulb. As the pressure goes up, the temperature goes up. So my thermometric parameter in this case is the mean gas pressure, and we call this a constant volume gas thermometer. By the same token, the temperature can also be proportional to the volume of gas in a thermometer. We call this a constant pressure gas thermometer. All other kinds of examples, we can talk about, for example, resistance thermometers, where the electrical resistance is proportional to the change in temperature of a system. So these are all ways, and there are many others, optical pyrometers, for example, for detecting very high temperatures. These are all examples of there's some physical attribute of this device that has many fewer degrees of freedom than the systems in question. That enables us to set up a proportion where whatever attribute it is proportional to the temperature of the systems involved. And this is what we call a thermometer. What we want to do now then is to say, let's bring back our discussion of beta again. We've said that in thermal equilibrium, if A and B are in thermal equilibrium, that means that beta sub A and beta sub B have to be equal. We have defined then, as we said before, 1 over K times beta as T, and that's what we call the absolute temperature. Later on, we'll refer to this as the Kelvin temperature. As you've probably learned in numerous physical science classes before, the Kelvin temperature is just 273.16 degrees higher than the Celsius temperature. It's one very simple way of computing the absolute temperature or the Kelvin temperature. So some of the properties, 1 over kT, as we said, is is defined as beta, and that's equal to the log, derivative of the log of omega with respect to E. So it's a statistical, notice, we're using, on this right-hand side, this is a statistical expression that tells us about absolute temperature. There were no hot and cold about it. It was just, we derived this from purely statistical means, which is fairly interesting. On the other hand, omega is a generally rapidly increasing function of energy, which tells us that beta should always be greater than 0, and thus T should always be greater than 0 as well. We will show you an exception to that later on, and it's a fascinating exception, but we won't talk about that just yet. One of the other things we want to remember is that omega of E is proportional to energy to the power of the degrees of freedom of the system. So that means that if F is a very, very large number, in other words, the system has many, many degrees of freedom, the number of accessible states is going to become enormous as energy gets larger. We can take this a step further. Let's take the log of omega. I can write that as F times the log of energy plus a constant to relate to the proportionality, so that when the energy is at its maximum value, in this case the mean energy of a large system, we can say that beta is equal to d log omega dE, roughly equal to F over E, which says 1 over kT is equal to F over E, number of degrees of freedom over the energy. Or we can twist this all around and say that the mean energy of a system divided by the number of degrees of freedom is equal to kT. This is a very primitive expression of what we call the equipartition of energy theorem. We will cover this later, but this is the first exposure you've had to it. As it turns out, it only works for classical physics. Once we go into the quantum realm, this thing will not work. But for now, this turns out to be actually a fairly easy way of calculating a mean energy. If I know the Kelvin temperature or the absolute temperature, K, by the way, we didn't really mention this. K is what we call Boltzmann's constant. Maybe we have, after Ludwig Boltzmann, a very pioneer in statistical mechanics, and that's equal to 1.38 times 10 to the minus 23. In our units, joules per Kelvin. If we find a system of units where temperature is dimensionless, then we notice that Boltzmann's constant would just have units of energy. The interesting thing about absolute temperature is it also tells us what direction heat has to flow. So the temperature that has the system that has a lower temperature is going to have heat flow to it from a system that's at higher temperature. Very interesting, kind of an indication of how natural processes occur. And let's play with this a little bit. Suppose I have, again, my two systems, A and A prime, and I have heat transfer between the two systems such that beta and beta prime are not equal. Let me write the condition that the entropy must increase in this way. So d log of omega of E dE times E final minus E initial plus d log of omega prime dE prime times EF final prime minus E initial prime must be greater than or equal to 0. that is to say then that beta initial minus beta initial prime times Q must be greater than 0. These guys are beta and beta prime. Specifically, it's the only interaction is the thermal interactions. There's no work, no external parameters changing. Therefore, this change in energy can only be thermal energy. So therefore, we have this condition. That means that if Q is greater than 0, it must be that beta initial has to be greater than or equal to beta initial prime, and T initial must be less than or equal T initial prime for this to work. All we're saying is that positive heat absorbed by the system, which is at the lower temperature. Warmer system is at a higher temperature, colder system is at a lower temperature. So this is an indication then of temperature and the coldness or hotness of an object. Let's bring back the notion of the heat reservoir. Remember what we said the other day? Heat reservoir is a system that has many more degrees of freedom than the system in question. So maybe this is A, we'll call this A prime as my heat reservoir. One of the other things we can say about this is that we can specify the reservoir by saying, no matter how much heat I add or take away from the reservoir by the system, I do not change the temperature of the reservoir. What that's saying then is that we know that the energy of our system, mean energy of our system, is going to be far less than the mean energy of the reservoir. So this is essentially like saying, suppose I took an ice cube as my system and dropped it into the Pacific Ocean. You don't think you're going to change the temperature of the Pacific Ocean very much by dropping one ice cube in it. So in that case, the system is the ice cube, and the Pacific Ocean, of course, is the heat reservoir. Let's look at this a little bit more quantitatively, though. Suppose my reservoir has something like omega prime with E prime accessible states. So a whole lot of accessible states. And let's say it absorbs some heat, Q prime equal to delta E prime. And it's absorbing that from system A. Let's express the change in the log of omega prime of E prime in a Taylor expansion. So I can write it in this way. I can say the log of omega prime of E prime plus Q, the amount of heat that it absorbed from the system, minus the log of omega prime of E prime. So I'm looking at a change in the log number